We're on covalent bonding number 3. We're going to look at naming molecules, naming acids, and naming oxyacids as well in this video. So, naming molecules. We're going to start off with naming binary molecules. And a binary molecule is just a molecule that only has two different elements. So, something like dinitrogen monoxide would be a binary molecule. And we've got a set of rules for naming binary molecules. One thing you'll see in all of my instruction, all of my videos, anytime I have a box around something, it's something that's really important, something that's going to affect you later on. And when I'm taking notes for my own personal reasons, I always put boxes around things that I'm definitely going to need to know down the road. So the 3 rules. Rule number 1, the first element in the formula is always named first using the entire name. So if we have CO2, that's carbon something. You probably know what the rest of that is. But rule number 1 says that that C is going to be called carbon. Rule number 2, the second element in the formula is named using the root of the element and adding the suffix "ide." So we already know that the first one is carbon. We know that second element is oxygen. But now we know that we need to change that to "ide." So it's carbon something oxide. Now if you need to write these rules down, just pause the video and write them down, and you can just play when you're ready. So the final rule, the prefixes are used to indicate the number of atoms of each type that are present in the compound. So what that means, if we go back to this, we've got carbon and 2 oxygens. We know it's carbon something ide. That something needs to tell us how many oxygens there are. So we've got carbon dioxide. Now, here's why it's not called monocarbon dioxide, because the rules tell us that the first element never uses mono. So if we don't have mono at the beginning of a binary compound, we know that there's only one of that first element. Otherwise, we need to state what there is. If there's more than one of the first element, we need to put how many there are, like di or tri or penta, and we'll get to those in a second. If the element begins with a vowel, sometimes drop the final letter in the prefix. That gets a little bit confusing. Generally, if it sounds funny when you're trying to name it, it probably is wrong. And several of these examples in here, I think you'll start to get used to this whole naming process of putting prefixes on there. I've got this whole list. I'm not going to go through the whole thing, but these are the prefixes in covalent compounds. If we only have one of something, it's mono. If we have 2, we put di, 3 tri, 4 tetra, 5 penta, and we won't use the other ones hardly at all. In fact, we'll use about 1 through 4, and then occasionally hepta for 7. You'll see some exceptions with that one. Let's name a few of these. We'll start off with CCl4. That C tells us we're dealing with carbon. And this Cl, the second rule, tells us we need to change that to ide, so it's going to become chloride. But we need to say how many there are. And if we go back to the prefixes, this would be tetrachloride. Now remember, we don't put mono on the first one, so it's not monocarbon tetrachloride, it's just carbon tetrachloride. Let's look at the next one. We might have to look AS up on the periodic table, but it is arsenic. There are 2 of them. Because there's 2 of them and not 1, we need to put a prefix with that. So di is the prefix for 2, arsenic, and then we've got oxygen for the next molecule, and there are 3 of them. So we need to say trioxide. Don't forget, we have to change the ending of these when we're making them into a molecule. We look at the next one, we've got carbon and we've got oxygen, remembering the rule that says we don't need to put mono if we only have 1, so this is going to start off as carbon, and we only have 1 oxygen, but even though we only have 1, the second element always has to have a prefix. So it's going to be monoxide. Again, here's kind of that one exception to the rule. We don't put monooxide, we put monoxide. So we drop part of the prefix. That's just something you have to get used to. Next one down here, we've got 1 sulfur and 2 oxygens. We don't have to put monosulfur, we just put sulfur. and we have 2 oxygens, so we use di, and we change that to oxide. Last one, we've got 1 nitrogen. We don't need to put mono. And we have 3 fluorines, so we use trifluoride. Those are pretty self-explanatory. And you could go through and do a whole bunch of examples of those, and people catch on pretty quickly. The trick is when we start running into acids. You have to be able to identify the acid, and then you have to be able to use a whole new set of rules when you run into an acid. So let's look at naming molecules and naming acids. First of all, what is an acid? An acid is anything that has hydrogen ions floating around in solution. So this is when you have essentially just a proton floating around inside an aqueous solution, so dissolved in water. The more of those hydrogen ions that you have, the more acidic it becomes. So this is what an acid is. That's going to be important to remember, that we're dealing with a hydrogen. We'll get to bases a little more later on, but just so you know, a base is actually a hydroxide ion, which is an oxygen and a hydrogen together that has gained an extra electron. So the more hydroxide ions we have in a solution, the more basic that solution is. Now if you looked at these, it kind of looks like if they came together, we would be forming something that had 2 hydrogens and 1 oxygen, which is why when we're dealing with the pH scale, and that's a whole different lesson, these even out at a pH of 7. That's neutral. Something that's very acidic has a pH of 0. Something that's perfectly basic has a pH of 14. We combine those together, we get a pH of 7. But that's for a different lesson. Let's focus in on acids and naming acids for our purposes here. When we're naming acids, again, we're looking at any compound that produces hydrogen ions in solution. So HCl in solution makes hydrogen ions in chlorine, and that chlorine will typically go attach itself to something else, but just so you understand what's happening with the chlorine and the hydrogen. And the more hydrogen ions we have in the solution, the more acidic the solution is. Now the reason I have a brain down here is when it goes back to naming, anytime you see a hydrogen at the beginning of a formula, it should throw up red flags on your brain. Big time. Because all those rules I just showed you, those nice 3 rules, we went through examples on one slide, you're feeling really good, you know how to name binary molecules. Now we have to change things up. If there's a hydrogen at the beginning, your brain should say, uh-oh, I need to do something different. So we have a whole different set of rules for naming acids. When we're dealing with binary acids, we're dealing with acids that have 2 elements in them, and these are acids that do not contain oxygen. It's really important that when you see a hydrogen at the front, the next thing you need to do is say, is there an oxygen in my acid? Okay, so the first ones we're going to deal with here won't have any oxygen in them because the acids with oxygens have a different set of rules. So we're back to our example. Hydrochloric acid is a binary acid. The rules for naming binary acids are pretty straightforward. We use the prefix hydro, as in hydrochloric acid. We use the root of the second element, like chlorine. We change that to ic at the end of the name, and we add acid, and we're done. So that's why it's hydrochloric acid. The hydro stands for the hydrogen. The chloric tells us that there is chlorine, and of course acid tells us that there is acid. Let's do an example. If we have HBr following these rules, we know that we need to have hydro at the front, so this is going to be hydro something. Br is bromine. We change bromine to ic, and we add acid. We end up with hydrobromic acid. Now, what happens if we see a hydrogen at the front, and then we also see an oxygen in there? So now we're dealing with oxyacids. And I apologize, this should say oxyacids. So, dealing with the oxyacids, again, I've got a brain up here because You see a hydrogen at the front, it should throw up red flags in your brain. And excuse me, an oxyacid is any acid that contains oxygen or a polyatomic ion of oxygen. For example, NO3 is nitrate, and that is a polyatomic ion. More clearly, you'll see that because that is supposed to be ionized. So rules for naming oxyacids. We do not use the prefix hydro. So if you see an acid and it doesn't say hydro at the front, you know that it is an oxyacid. When we see an oxyacid, we change ate to ic. For example, up there in our nitrate, or the one I have right here, HNO3, this is nitric acid. Because the NO3 is nitrate, when it becomes an acid, we change ate to ic and add the word acid. Likewise, sometimes our polyatomic ions end in ite, like nitrite. So ite changes to us and we add acid. So this would be nitrous acid. Now, what if you don't know the polyatomic ions? Well, you're going to have to look them up, and I have it right here. This is straight off of Wikipedia. If you go there, you can get the same list. You can look all over the internet, and you can find all sorts of polyatomic ions. I just have some of the anions up here. And we'll deal with some of the cations later on. Let's name a few of these. We see HI. First thing it does, it throws up red flags in our brains. Next thing we do, we look for oxygen. There's no oxygen in there, so I use that first set of rules, which tells me I put hydro. And then I need to figure out the second element. It's iodine. I change it to ic, so it's iotic or iotic, and then I add acid. Let's go to the next one. I have a hydrogen at the front, red flags in my brain. The next thing I do, I look for an oxygen, because this is going to help me determine which set of rules do I use. I see an oxygen there, so I know I'm dealing with an oxyacid. I do not put hydro at the front. Instead, I find out what polyatomic ion is this. I see it right here. Chlorate, ClO3-. So, I don't put hydro. Instead, I know it's 8. 8 goes to ic, and I add acid. So this is chloric acid. Now let's look at the next one. Again, red flag, it has a hydrogen. Second red flag, it has an oxygen. So I need to look up the second part of it, and I see it right here. It's chlorite. So ite goes to us, and I add acid. This is chlorous acid. Next one. I see a hydrogen at the front, and that throws up a red flag. I see an oxygen, that throws up a red flag, and now people get concerned because they see two hydrogens. They think they need to put dihyd. You don't have to. This is an acid, so you follow the rules for naming an acid. Because there's an oxygen, I don't even have to put hydro at the front. I just need to find out what SO4 is. And SO4 down here at the bottom is the sulfate ion. I'll explain to you in just a bit how we end up with that too, but for now let's just worry about naming it. Because it, excuse me, because it is sulfate, 8 goes to ic, and I add acid. This is sulfuric acid. Last one down here at the bottom, we've got H2S. Again, red flag, there's a hydrogen at the front. I have to follow the acid naming rules. Then I see that there is a sulfur. Again, there's no oxygen, so I have to put hydro at the front. Hydro. And the sulfur I change to sulfuric. And add acid. Now, one thing to notice, that hydro at the front is very important because hydrosulfuric acid is very different from sulfuric acid. This is a flowchart I've put together that I think will help you out. It tends to help most people out. If you need to write these things down, just pause the video and you can write it down. We're dealing with covalent bonds in all of the examples. So we can just go down this flow chart. First thing we need to do is figure out, does it form an acid? How do we know that? Well, generally if it has a hydrogen at the front, it forms an acid. That's not always true, so you have to be careful. We've got some other things that can form acids that don't always have the hydrogen written at the front, but general case, most of what you're going to run into will have a hydrogen at the front. So, does it form an acid? If it does not, then we're going to use these rules right here for naming a binary molecule. If it does, then we need to decide, well, does it have an oxygen in it? If it has an oxygen, yes, then we're going to use the oxyacid naming. If it does not, then we're going to use these. So this is all of those rules put together in one. Let's look at nitric acid and nitrous acid, working our way backwards to write out the formula. So we've got acid. We're definitely dealing with an acid, but we don't have hydro at the front, which means these are our rules that we need to use. We know it's an acid, and it ends in ic. So if we look really carefully at that part right there, it says that ic used to be 8 because 8 turned to ic. So right now it is ic, and we know that ic used to be 8. Well, what does that mean? We've got nitr, and 8. We've got nitrate. So all we have to do is find nitrate, which I can see it right here. Nitrate is NO3 minus. Nitrate is NO3 minus. And we know that there has to be a hydrogen at the front because it's an acid, and hydrogen always makes a plus. That 1 plus and that minus, they're going to even each other out, so I can get rid of those. This is nitric acid. Now, what if we look at nitrous acid? Again, it is an acid, but it doesn't have hydro at the front. Because it doesn't have hydro, we know that, we're dealing with an oxyacid here. And we already know that that must have been nitrogen, but now it ends in us. If I look down here, I can see change ite to us. So if it's us now, it used to be ite. So this used to be nitrite. I come over here and find nitrite, and I see it right here, NO2 minus, NO2 minus. Now we know it's an acid, so it has to have hydrogen at the front, and hydrogen is just a plus. This plus and this minus, they're going to even each other out. I keep showing you that because there are some examples where those will not even each other out, and this is nitrous acid. I've got a bunch of the chlorine ones up here on the screen. I'm just going to work through them very quickly to show you how it works. Every one of these, notice there's no hydro at the front. This hypo is different than hydro, and this per is different. They don't say hydro, which means they've got to be an oxyacid. So I see perchloric. Well, there's a whole bunch of naming rules about per and ate and ite and hypo. I'm not going to get into those because I have them listed over here, but it's something you may want to look at down the road. So perchloric, ic used to be 8, so this must have been perchlorate. That says perchlorate, I apologize. It must have been perchlorate at some time. I come down here and I see perchlorate is right here. So I've got ClO4 minus. And I know it's a hydrogen, and hydrogen is a plus, so if I make some room here, this is HClO4. Let's look at chloric. So chloric, again, it does not have hydro at the front, so it's got to be an oxyacid. It still has ic. If we come down here, 8 turns to ic, so this used to be 8, chlorate. We find chlorate over here. Here's chlorate, ClO3 minus, ClO3 minus, and there used to be, or didn't used to be, there still is, there's an H plus ion at the front of that. Let me just clean this up and write out exactly what we have. We have HClO3 for chloric acid. Let's do the next one. We've got chlorous acid. Again, no hydro at the front, and us used to be ite. Us used to be ite, so this used to be chlorite. I find chlorite right here. It's ClO2 with a minus charge. Hydrogen has a plus charge. If I clean that up and write it correctly, we have HClO2. Again, I don't put the charges on there because those two, when they combine together, those charges even out. That's the whole reason that they bond together. And the last one here, I've got hypochlorous. Chlorous. Again, that us down there used to be ite, so this used to be hypochlorite. Promise that's what it says. I see hypochlorite here, ClO minus. We know hydrogen is H plus. Those are going to even out. Let me rewrite it. HClO. That is hypochlorous acid. Got one more I want to look at, and that's sulfuric acid. It'll show you why I've been putting those ionic charges on each of the atoms as we're writing them out. So it doesn't have hydro at the front, so that means it must have an oxygen. I have to use these. It ends in ic, which means it used to be 8, so this used to be sulfate, and I know it's an acid. I find sulfate right down here. Sulfate is SO4 2 minus, and we know that hydrogen is an H plus ion. Now this is where they don't even out. This sulfate has a 2 minus charge, which means it has 2 extra electrons, and this hydrogen ion doesn't have an electron, so it's missing one. In other words, this number and this number have to even out. The only way to do that is to put another hydrogen ion when these combine together. That means now we have 2 positives to even out our 2 negatives. Let me erase this and show you. That means we have to have 2 hydrogen ions bonding to this SO4. So this is sulfuric acid. And in the next video, we're going to look at covalent bonding and molecular structures and how they turn into 3-dimensional structures when we start to look at them. And then we'll look at polarity within those structures and intermolecular forces that hold all the different molecules together. So good luck.